Ladies and gentlemen, I'm very glad to be invited here and so to talk about a very brief presentation for sustainable resources recycling system, and also to talk about the circulation technologies to be applied for achieving the environment-friendly resources recycling. First of all, as you know well, the 3R concept for sound material circulation society, this 3R initiatives was proposed by the Japanese government 2 years ago in the Sea Island Summit. But this concept is basically is followed by the law of basic law for establishing the recycling-based society. It was established in 2000. And of course, you know, the 3R concept is very well known, and excuse me. Yes. The first R is the reduce, the amount of waste, and second one is the reuse as product and or parts, and this is, in other words, the functional recycling. And third one is the recycle. This is in actual material recycling. Recycle as functional materials or raw materials. And also these two kinds of issues again is followed by these 3 R's: energy recovery from waste materials, and also detoxification of the final waste. And here, I would like to talk that this 3R concept is from the viewpoint of very, very basic and scientific viewpoint. Next, please. Oh, okay. This is the basic concept of 3Rs and the technology required in each step. Let us start just in natural resources here. And the natural resources can be produced, they are raw materials by several recirculation technologies, and raw materials and functional materials can be produced from the raw material. Also, this description of how circulation I can tell you later. And the parts, product by the technologies of manufacturing and assembly technology, and so we consume these kinds of many kinds of products and so enjoy it. But after consumption, of course, waste materials, a huge amount of waste materials have to be generated. Then, how to recycle this kind of waste materials? We have many loops have to be applied. And the first one will be the product loop. But this loop have to require for example, new technology must be there. Self-diagnostics and self-repairing technology have to be applied to achieve the product loop. And also, parts loop, the second choice will be the parts loop. Then the technologies to be applied is the disassembly technology and the parts circulation technology. And so these two loops we call reuse, in other words, functional recycling. But several product and parts have to be degraded and then no more use for us. Then after that, the material recycling has to be applied. The first step is the functional material loop. This loop is also the technology should be applied is in a soft and hard, and then many kinds of hard circulation technologies, and also raw material loop to achieve raw material loop and hard circulation technology. Hard is in other words a chemical circulation, and resources loop also. This is a final loop to be chosen. And the technology required will be the transformation, and such as in a combination or some other and melting or such kinds of technologies have to be applied to achieve this resource loop. But the first priority is in the reduce. And so this concept is have to be applied all of these kind of stages. This is, of course, to reduce the amount of material flow in our economical system. This is the first priority. And then the reuse and recycle system to be the next one. Next please. But very famous, Bauta Jungbauer, probably the German researcher knows, very famous researchers told us several years ago, recycling virus. We have to prevent this concept. Probably in 20th century, and so our industry is like this, mass production, mass consumption, mass disposal, and in these several decades, we are searching new technologies for sometimes mass recycling. And in these several years, probably mass waste trading is also, for example, Japanese government has now trying to create a new system of the international, the world, international waste trading system. Of course, probably Korea is also in the same situation, but the huge amount of waste materials generated in Japan is now transported to China because of the low cost of the processing. But this mass system is good or not to achieve their sound material circulation system? Of course not. We have to prevent this kind of bad cycle. And how the business should be in this sustainable recycling system? Probably this mass concept is going to eco business, ecological business. This is not our choice. Our choice must be business for ecology or environment. And some American and the researchers group is very famous, an industrial ecology group. Probably 10 years ago, this group established and from, I forgot the name, okay, very, very famous university. But this concept is also the same as the zero emission, original zero emission concept and created in Japan. How to create these kinds of businesses? This is the concept of my talk. Please. This is very, very simplified diagram for the circulation of materials. Start with the natural resources, and through some production activities, we produce some products and consumption, then waste, and how can we recycle these waste materials? Very many kinds of groups we have, such as in recirculated to the product. This is the concept of reuse, and going to the middle stage of the some production stages, and also waste materials can be treated just like natural resources. What kinds of rules is best for the sustainable recycling system? Of course, objectives of the resources recycling is, we have two big objectives. One is resources conservation. The other one is environmental conservation. Resources conservation, I mean prolong the resource life. The first one, probably no one suspects. By the recycling activity, probably the resources can be prolonged, the life can be prolonged. But is it true? The recycling activities can contribute the environmental conservation? Probably some of them is no, but some of them yes. What is the boundary condition? What is the boundary condition? This is very, very simple concept, but boundary conditions should be like this. From any human activities, environmental impact have to be generated, even from recycling activities. Then, if we choose this loop, by using natural resources, we have to generate two kinds of environmental load from production stage and also from consumption stage. The driving force of this material circulation is, of course, consumption. And to reduce the material flow in consumption stage is the best way, of course. But it's very, very difficult because we are human beings. But then here we assume the consumption is, the material flow in the consumption stage is constant. Then by utilizing the natural resources, we are generating two kinds of environmental load from production and from consumption. But why? How? In this recycling stage, in the recycling stage. Another two kinds of environmental load have to be generated from recycling stage and also consumption stage. Then, if this loop should be environmentally conscious or environment-friendly recycling, the boundary condition is L3 must be lower than L1. It's very simple. What about with this L4 loop? Probably L4 plus L1 dash should be smaller, lower than L1. And what about the waste materials going to the same as the natural resources? Recycling activity, environmental load generating in the recycling stage should be zero for achieving environmentally conscious recycling. Is it possible? Of course, no. Theoretically, no. Then, waste materials should be, these kinds of routes should be chosen. But if we have no recycling system, probably huge amounts of final waste materials have to be generated. Then we have to put this environmental load on these equations. Then this boundary condition is a little bit not so strict. For example, dioxin generation and sulfurium generation and then heavy metal ions disposal. Probably this is very, very serious, generated serious and environmental load. This is the boundary conditions of the environmentally conscious recycling. But this is very, very simple concept. But problem is what is the environmental load? What is the environmental impact? It's very, very complex and very, very difficult to be solved. But from the very basic and scientific viewpoint, probably this is only the solution. Now, from now, I'd like to talk about that next, please. In the production process, we divided into several stages, and horizontal axis, the processes to be proceeded. Then the vertical axis, we put some value. In the first stage of the processes, any processes started with the resource value. Then, while proceeding the processes, the resource value can be transformed into some product value. Then, finally, after the total processes, we can create some product value from a resource value, but not 100% value can be recovered. Only some of them can be recovered by any actual processes. The last one is here, uselessness. And These processes can be defined as we can produce some product from resources. But in other words, probably we can create some reality as a product value from the possibility as a resource value. What's the difference of the resource value and the product value? What is the difference? In my consideration, probably product value has a higher concentration of some specific element, specific component, and also have a higher configuration in, for example, in macro stage, just like a parts configuration, and in micro stage, in an atomic configuration. But anyway, some concentration of some component and the configuration of some parts or elements. This is the difference of the resource value and product value. And how we can define some quantitative index for this concentration, differences of the concentration and the configurations. What is the index? It's very easy from the scientific to solve this very basic scientifically solution. It's just very. You're also very familiar. The index is the entropy piece. For example, in ion making process, before reaction, we have iron oxide and some reductant and also fuels. Then we can create almost a pure iron from the iron oxide. But we need a reductant for this reaction and also fuel, which is low entropy state, pure iron and iron oxide. Of course, this one. This is the product value. This has the product value. This is just the resource value. Then we create some product value, in this case pure iron from iron oxide. But to produce this low entropy state, in this reaction, the reductant have to be transformed into carbon dioxide and water vapor, and also fuel have to be generated as their low temperature heat or carbon dioxide. This state is very high entropy state. And so, which stage is, in totality, which stage is more higher or lower entropy? Of course, after reaction, this stage has much higher entropy in total. And then, here we can define the production process is to produce very small amounts of useful product, low entropy state, at the sacrifice of huge amounts of entropy generation. Probably this is their scientific solution of their to define the product production process. Next one, please. Next one, please. Then we can define boundary conditions of the I mentioned previously, environmentally conscious recycling. The environmental load can be replaced as the entropy generated in each stage. Then, environmentally conscious or environment-friendly recycling can be defined as the low entropy generated. The entropy can be also defined as the environment disruptive potential, not the real one, but the potential. The entropy generated in resource utilization process must be lower than that in regional resources utilization process. This is the definition of their environmentally conscious recycling technologies. Then we can go back to the 3 R's concept. The reduce, from this scientific viewpoint, the reduction of the amount of waste materials is very, very reasonable. Priority number 1, of course. Material flow rate should be reduced. No one can deny the priority number 1 process. And second one is their functional recycling, reuse, because this state, product or parts has a very, very low entropy state in micro or macro scale, because they have a function, not just a material. Then reuse has a second priority. And third one is material recycling. But in this stage, we have several stages. For example, functional material has lower entropy than low material, and then just a resource. But this resource is very, very narrow term. This is a concept that of the 3 R from the scientific viewpoint is my consideration, please. Excellent. Then, from this consideration, we can put this kind of a diagram. This is a conceptual diagram of recycling process and global problems, or global processes, probably shown later. Okay, let's start here. In this diagram, lighter color represented in the state of higher entropy state, low level state. Start with the natural resources, for example. And so we create some product, and dark color one is the low entropy state, very high level state. But we can create low entropy state from high entropy state. But we need, and after consumption of the product, reuse system must be the first choice. But after consumption, finally, this product have to be going down to the just raw material. Then we can put some recycling technology here to upgrade and to produce some product again. Then this black circle can be circulated like this. And if we watch this black circle, only this black circle, no problems we have, no problem. But in each stage for upgrading, we definitely need some new feed as material or energy. Then this new feed material or energy have to be transformed into very, very high entropy state as a final waste, uselessness. And also, in this process, in each production or in each recycling process, we have to generate much amount of entropy from these processes. Then, this black circle, in the black circle, this is human system. But outer part is a natural system. In this century, we have 3 big problems. The first one is population problem. This is in the human system. The problem is in human system. Probably it's very difficult to follow by scientists. Next one. And the second one is resource problem. Resource problem. If we watch only black circle, no resource problem we have. But to continue this circulation, we need new feed from outer systems, natural systems. this is the real resource problem. Not this resources, another resources problem we should have. Then another one is the final waste problem, environmental problem. Environmental problem probably divided into two kinds. One is the final waste problem, such as heavy metals or dioxin generation or something. But another one is this. Another environmental problem is the potential problem. Very huge amounts of low temperature heat or low concentration toxic element can be probably diagnosed. No, not diagnosed. Okay. In the atmosphere, in the water, surface water, on groundwater also. But at that time, we cannot recognize this is toxic or not. For example, dioxin. No, for example, fluorine or carbon dioxide. 20 years ago, no one knows such kind of component is toxic in the global system. But this is a potential problem. Okay, next one, please. 5 minutes. Okay, next. Next one, please. Okay, this is the example. The separation technology. I have to talk about also the separation technology. And from this kind of constellation, we'd like to think about the separation technologies. The waste materials, start with waste materials, combination or mixing and size classification, and several the separation technologies have to be applied to upgrade the material. Then the separation technology, compositional separation technology, can be divided into the two kinds. This is I just created this term, and soft separation and hard separation. In other words, soft separation can be replaced in physical or mechanical separation, and also hard separation can be replaced by their chemical processing, melting or dissolving in some solvent. And soft separation is just like a solid separation, solid state separation. The property is the neutralizing and solid property without destroying atomic configuration. And then the theoretical, this kind of separation need no energy, theoretical. If we can separate force statically. But hard separation process, by dissolving or melting, of course, destroying the atomic configuration, of course, require activation energy, theoretical. Then environmental impact is lower in the soft separation, but high in hard separation. But what about theoretical background? Solid separation has very poor theoretical background because solid materials, no two solid materials is the same, completely the same. This is a heterogeneous separation process because the theoretical background is very low compared with the hard separation. Then the reliability is very low in soft separation, but high in hard separation. And also, what about the toxic element? Soft separation cannot change the state. And if toxic one is, of course, as they are after the separation. But hard separation is possible to be detoxified because destroy the atomic configuration. We can create another component from the raw material. But sometimes we can make a mistake to toxify. For example, dioxin is also a very, very serious example. This is two kinds of separation technology, but to create effective environmental conscious recycling process, two kinds of separation technologies have to be combined very, very to utilize each advantage of the processes. Next one, please. Okay, next. Okay, this is one example. One of our research work is to recover precious metals, platinum group metals from the combatant. This is the diagram of the combatant in the polish section. Cordierite is existed like this in the form of lattice. Then the alumina layer involving PGM is covered. This is the structure of the combatant. Please. Next one. And next one, please. Yes. Solid separation in the target system is like this. For example, the liberation size of cordierite is almost several 10 micrometers, the particle size, liberation size. And what about PGM liberation size? Is probably several 10 nanometers, very, very small. And after dissolving in solvent or melting, liberation size of iron is several angstrom, very, very fine, too fine. This is, of course, much lower entropy state and very higher entropy state here. Which one we can choose? Now, very famous Rose process developed by the Dowa mining company, a Japanese company, is applied this kind of state. But our approach is the separation in this stage, please. This is the concept. After combination of the catalyst, combatant, now the Rose process directly going to some metallurgical or chemical process. But if we apply some appropriate combination, we can divide it into the several parts. This one, coarser size, concentrated only cordierite, and finer size only aluminum. Then involving a PGM. And this is directly going to the metallurgical process. But in a middle size, cordierite and aluminum mixture, we can apply some solid state separation technology such as flotation to concentrate the aluminum. Then going to the metallurgical process. In these processes, we can reduce the energy required in the process. Is 60 to 80% energy can be reduced. This is the concept, soft separation, the mixture, combination of soft and hard separation processes. Okay, now it's time to finish my talk, but this concept is very, very basic scientific approach. But the exceptions is in the real process is exceptions many. For example, toxicity cannot be defined in this concept. But exceptions very, very many. But very basic scientific consideration, I would like to know some Korean colleagues. Thank you very much.